So the purpose of my talk will be first to present you what are the intermediate data product of geotraces, and also how recent results obtained in the modern ocean can help to constrain the paleo application. Geotraces, the mission of the program Geotraces is to establish the distribution of the trace element and isotopes as broadly as possible in the world ocean. For doing that, we operate sections, and regularly we edit intermediate data product. What is an intermediate data product? This is an open source database of results that have been obtained in the framework of the Geotraces cruise. The first one was released in 2014, so it gathers the data that have been obtained for the first 4 years of the program. These data, they have been intercalibrated, validated, and the quality control was very, very rigorous. So you have a set of data, open source, available. In addition, we also, in this data product, propose an electronic atlas that allows describing the parameter along sections, as it is shown here for the iron, and also on 3-dimensional plots that are animated and that allow to better constrain the behavior of your tracer. This summer, during the Goldschmidt conference in Paris, we will release the IDP, Intermediate Data Product 2017. That means that we will have 7 years of data of the Geotraces program. To give you an idea, today we already sampled more than 1,000 stations were collected and documented in the ocean through the program Geotraces. So in order now to discuss the interest of working with this high-resolution modern data on tracers and proxies, I selected 3 famous proxies. The first one is cadmium as phosphate paleoproxy. So the story, the seminal work of Headboyle, was to establish that dissolved cadmium in seawater is related to phosphorus here with a linear relationship. So the main idea was if you have the CD cadmium, which is obtaken in foraminifera, like this one, for example, then by measuring the cadmium to calcium ratio in the forams, you can estimate the cadmium in seawater. And thanks to this relationship, you will reconstruct the phosphate in the seawater, which was broadly used as wonderful tracer, both for paleoproductivity and also for paleocirculation. However, this clear paradigm is challenged recently by the work of Kay, who gathered more than 180 stations from high historical data, Cliver and Geotraces sections, and they established that there are some variation in the cadmium to phosphate ratio, as illustrated here. So this is the latitude there that you see, equator and the north and the south. And the cadmium to phosphate ratio represented here for the surface water, the dissolved phase, it shows that whatever the ocean, Pacific is in red, Atlantic in blue, Indian in green, you have higher cadmium to phosphate ratio in the surface water in the northern part and southern part compared to what is observed at the equator. So to understand why, you need to quantify the factors and control the cadmium to phosphate ratio in the particles and the cadmium to phosphate ratio in the surface and deep water, how it impacts this distribution in the surface and deep water of the ocean. To understand what's happening in the particles, the simple biological scheme is that cadmium to phosphate in the dissolved phase is obtaken by the biology here in the particles. These particles created there are sinking, they are degraded, they release that cadmium and phosphate, increasing the concentration in the deep water. This is refeeding the surface water, and the loop is operating. And what was observed by this author is that the exported particles in the high nutrient low chlorophyll areas have a display cadmium to phosphate ratio, which is more than twice than of the non-high nutrient low chlorophyll area. And this is directly related to the fractionation during the uptake of the cadmium and phosphate from the dissolved phase to the particles, this fractionation factor is definitely higher in the areas that are very productive, high nutrient, low chlorophyll. So they have a lot of nutrient, but they are not so productive. So what did these authors? They coupled this result in the 9-box model to check first that the model output was consistent with their data, which was the case. And they also played model experiment, changing the high nutrient, low chlorophyll condition in the Southern Ocean, showing that this impact dipped cadmium to phosphate trend everywhere in the ocean. So this mechanism could bias the use of cadmium as paleoproxy, because the coupling of this biological activity and the OGCM is showing that you can have a perturbation of this imprint. The second work I would like to underline here was proposed by He et al. In marine chemistry, the same year as Kay. And they also used geotraces data that were allowed to follow the line here of the South American coast and data from water source regions. And what they show is that this cadmium to phosphate ratio in the dissolved phase is perturbed with some data that are low, that display lower cadmium compared to what is expecting from the classical relationship, and they interpret that as an influence of water advected from the Angola Basin. This water is cadmium depleted, low oxygen water, and it also cadmium depleted, and so this will influence the cadmium signal along this section, and so this will impart a cadmium depleted signature to the equatorial intermediate waters that will be distinguished from them from South intermediate water. And so what is the warning of this author is that there can be the offset to lower cadmium concentration highlights the potential role played by the oxygen-depleted zone in the global oceanic cadmium distribution. And because we know that the past extinction of the oxygen-depleted zone might have changed, this can also change the imprint of the cadmium to phosphate. Let's now discuss zinc as silica paleoproxy. And I would like to invite you to read the nice paper published by Vance and co-worker in Nature this year. This author, they propose first to have a look to 3 profiles representing the 3 main basins: blue, the Atlantic; green, the Indian; and pink, the Pacific Ocean. And these profiles here are representing the silica and zinc profile and the phosphate profile. And what is striking is that you have similar silica and zinc profile, so similar that you cannot distinguish them, whatever the ocean, while they are decoupled from the phosphate profile. This relationship conducted many people to think that silica and zinc are coupled, so coupled that zinc was supposed to be the proxy of silica and in the diatom skeleton. And actually, the work of Ben Twinning and his colleague using XRF, so watching very precisely at the cell, showed that zinc is collocated with phosphorus and not with silica in the diatom cell. So there is a paradox. How do you obtain such a beautiful coupling between silica and zinc if they are not coupled in the cell? So this is a bit tricky, but I will try to explain you the story here. So here you are in the Southern Ocean, 65 to 40 degrees south. This box is representing here the Antarctic surface water. And what this author have shown, so here you have polar front and subantarctic front. And they show that the diatoms are requiring a lot of zinc when they are building their organic part, more than 10 times than the other phytoplankton. So here in the surface water, you have an efficient silica and zinc stripping in the Antarctic surface water, and the particulate organic matter which is exported will export high zinc to P and high silica to phosphate ratio. So, but they have different regeneration scales, which here will not be critical because they are falling in the homogeneous circumpolar deep water. So whatever the depths of the regeneration of the soft part and of the hard part, you will have an input of high Zn to P and high C to P ratio here, and coupled again to a general circulation model, this author demonstrates that the zinc, so this will redistribute this zinc, silica, and phosphorus property in this general circulation model. And so they demonstrated that there is clear relationship between zinc and silica, but it's not due to the collocation in the diatom skeleton. It's due to these processes, so the specific diatom ecology and the ocean dynamic. The last example I want to show you, but I won't discuss it a lot because there are many talks this morning, on protactinium and thorium, and there are posters too. So first, what are this proxy telling us? The production of these two tracers, protactinium and thorium, are due to the decay of uranium isotopes. They are produced as a clock with a production ratio of 0.093. And once they are in the seawater, thorium is scavenging rapidly, while protactinium has a longer residence time. So when there are few particles in the water column, the efficiency of scavenging the thorium is more important than the one for protactinium, which has a time to be advected. And when you enter in higher productivity area, what is expected, and what was the theory until very recently, is that you will have a strong scavenging of the protactinium. So what is expected is that protactinium is scavenged in the opal belt. Actually, when you look at the geotraces section from the north to the south, here it's the north, here's the south, here you have the data, and you see that protactinium is very concentrated in the opal belt. So it's not what was expected. The dissolved protactinium did resist to the scavenging. And the consequence is that the protactinium thorium is almost constant along the North Atlantic deep water. So the fact that this tracer was used to trace the Mediterranean, the Atlantic Mediterranean overturning circulation, and also the advection of protactinium is questioned by this result. So is protactinium thorium a ventilation tracer, or are they quantifying scavenging by particles? Because they are broadly used, it's an important point to discuss, but I don't want to discuss them too much because later this morning you will have talk on this issue. And I also invite you to see the poster on this topic, poster 165, 172, other poster this evening, and of course the talk of this morning. To conclude, the numerous new trace element and isotope data that are acquired as part of geotraces which are validated and accessible as open source in intermediate data product represent a precious mine of information. The three examples that I showed here, together with the talk of Tachikawa this morning, and on protactinium thorium, the talk of Hayes and Gay poster, warn us on too rapid and blind application of modern correlations to paleoreconstructions. And coming soon, and don't forget that, in Paris this summer, we will release the IDP 2017 with definitely more data in all the ocean, and I thank you for your attention.
You use the expression for cadmium phosphorus, almost linearly related, but they look rather polynomial. What is the joker, according to you, there?
So this is also discussed in the work of Xi, and they suppose that this is the subantarctic mud water which is propagating a kick in the relationship. And that's something that will probably be more discussed also today, I guess, but also because we have so many new data now that we can have a better picture of this kick, which is known for a while. Yeah.
Hi, my name is Yingzhe. I'm a PhD student at Lamont-Doherty. Today, I will talk about how well neodymium isotopes trace AMOC mixing, a test in the Southwest Atlantic. Neodymium isotopes have been increasingly used to trace the Paleo-ocean circulation. Based on the modern ocean observations that the neodymium isotopic ratios effectively fingerprint different water masses. In this map of seawater absolute neodymium shows the systematic variability with the lowest values in the North Atlantic in red and the highest absolute neodymium values in the North Pacific in blue and intermediate values elsewhere. In addition, neodymium isotopes are not affected by biological processes, and the residence time of neodymium in the ocean is shorter than the ocean mixing time, which is long enough to allow neodymium to be advected by water masses, but short enough to prevent homogenization. Understanding how epsilon neodymium works in the modern ocean serves as a basis of its application as a paleo circulation proxy. And the GeoTraces program provides the opportunity to investigate how well, to what extent neodymium isotopes can be used as a conservative water mass tracer. During the cruise of GeoTraces GA02 Leg 3, we collected 272 seawater samples from 17 stations for neodymium isotopic analysis. For each station, we collected 16 samples from surface to bottom. The Southwest Atlantic is an excellent place to investigate how neodymium isotopes trace water mass mixing because the regional hydrography includes the major water masses involved in the AMOC. Here, the salinity section clearly shows the southward NADW, the northward AIW, and AABW. Another reason why we chose Southwest Atlantic as our study area is that there are potential sources that could add external neodymium to seawater and disturb the quasi-conservative behavior of epsilon neodymium. One of the sources is terrigenous, which is the weathered continental material delivered by river flux and aeolian dust. I'm sorry, what happened? Oh, sorry. In this surface map, the color dots show absolute neodymium values of river sediments and core top sediments. They reflect geological ages of the sources, the red color corresponding to the source of oak craton with low absolute neodymium, and the blue color corresponding to the source of young continent with high absolute neodymium. And the black dots are our seawater stations. So the question here is, will the seawater absolute neodymium be altered by the terrigenous sources and deviate from what we expect to see based on mixing? Here we show the absolute neodymium depth profile of selected stations. The absolute neodymium values for in the top 250 in the 250 meters in the blue area, they vary from -18 to -7, with lower values in the north and higher values in the south. And this variability is consistent with the continental variability and indicates the terrigenous contributions. And this shallow water variability is bigger than the variability in the intermediate water and deep water, which means that the shallow water, the influence of terrigenous inputs at the shallow water is not transferred to intermediate and deep water. So now I'm going to show our analyzed absolute neodymium data in an ODV section profile. Here it clearly shows the major water masses involved in the AMOC with southward NADW and northward AIW and AABW. When we compare this section with the sections of conservative water mass tracers, salinity, and phosphate star, we found remarkable similarity between absonidium and seawater properties at intermediate and deep depth. So we studied the intermediate and deep water in more detail by looking at hydrographic properties from the depth of AIW to the bottom. In this plot of potential temperature versus salinity, we used the rainbow color system to show different stations, with southern stations in violet to northern stations in red. And the black crosses in the plot, they're water mass end members defined from the World Ocean Atlas 2013 in the water mass formation regions. And going down the water column in the far south, they almost follow the southern source water, AIW, CDW, and ABW, with sniffs of northern source water. There is a progressively increasing influence of northern source water at middle depth. And for the northernmost stations at the equator, they show very strong influence of NADW, which consists of three components: upper, middle, and lower NADW. And the AIW signal decreases from south to north. Then we compared our absonidium values with the potential temperature. And there is, again, the black crosses are water mass end members, and the absonidium values are defined from the published data in the water mass formation regions. And there is a sequential change from south to north following the violet, green, and red curves, similar to the systematic meridional change observed in the theta S plot. And the loss of AIW signal is also seen here with decreasing absonidium. So to a first order, the intermediate and deep water absonidium values reflect the mixtures of main water masses. We want to further quantify to what extent neodymium isotopes can be used as a conservative water mass tracer. So the question here is how well absonidium reflects the water mass mixing. To answer this question, we calculated the predicted absonidium values based on water mass mixing. So each point is the mixing of three relevant end members. Take the blue point, for example, it's the mixing of ABW, CDW, and lower NADW. So for each sample, we calculated the fractional contributions from each relevant end member using the water mass mixing equations. Then we calculated the predicted value and compare it with the measured value. And here are the equations we use for the calculations. So these three equations, they're basic three-component mixing equations. With three equations and three unknowns, we can calculate the fractions. Now I'll show you our calculated delta absonidium values in a section profile. So the delta absonidium is the measured absonidium minus the predicted value, and the numbers, the value 0 corresponds to the green color here in the color scale. So this section shows that almost everything is close to 0, which indicates very small differences between measured and predicted values for the whole transect. The histogram of delta absonidium values show more quantitatively how well neodymium isotopes trace water mass mixing. Here the x-axis is delta absonidium. The y-axis on the left is the count number. On the right is the percentage. Within each interval, the samples at different depths are shown in different colors. It's green from AIW to upper NADW, red from upper to lower NADW, and blue from lower NADW to ABW. We calculated a total number of 174 intermediate and deep water samples for delta epsilon neodymium with a mean of minus 0.07 and one standard deviation of 0.61. About 51% of the delta values are within plus minus 0.25, which are approximately within the measurement error, and about 84% of the delta values are within plus minus 0.75. And this indicates that the measured epsilon neodymium values can be effectively predicted based on the water mass mixing. The Southwest Atlantic Transect is a part of the GeoTraces Atlantic Meridional Transect, GAO2, from 60 north all the way to 50 south. Here, I combined our epsilon neodymium data in lag 3 with Northwest Atlantic epsilon neodymium data in lag 1, published by Lambert et al. 2016. And here we can see that the agreement between the epsilon neodymium section and the salinity section is stunningly good. So to summarize, the seawater epsilon neodymium in the Southwest Atlantic Meridional Transect confirms its quasi-conservative behavior at intermediate and deep depth, and the measured epsilon neodymium values are effectively predicted based on water mass mixing. And the heterogeneous sources have major impacts at shallow depth, but they are not transferred to intermediate and deep water. Thank you for your attention.
Just one clarification. When you do the mixing, the three, is that just a multiple regression with the three, with all the data together? How did you find the coefficient? Yeah.
I mean, for the equations?
Yeah, yeah.
What's your question?
Yeah, just how do you determine F1, F2, F3?
How did I determine?
How
did I determine it's the mixing of these three?
Yeah.
So here, this is the potential temperature versus salinity, and the point is here. So basically, it's a mixing of these three MMers. Here, I'm just making it like more clear to see. But here, you can actually see it's the mixing of 1,
so
2, 3. Yeah, okay. Yeah.
Mark, is it really fast? Fast. Antarctic bottom or intermediate water is actually just about at the border of your bar where you said it cannot be used anymore. So in how far is Antarctic intermediate water really reliable? Or is it already affected by inputs from top?
You mean the... You mean here?
Yeah. It's almost 1,000 meters. The core, it covers the core of the intermediate water.
So the intermediate water is like modified from south to north, right? With increasing salinity and temperature and then also density. So it's actually like intermediate water is like this. I can show you the depth profile. You can see the change. It's the depth is decreasing from several hundred meters to about like 1,000 meters.
Yeah.
Yes.
So we're going to have to move on.
Good morning, everybody, and thank you for invitation. What I present today is realized during the NeoSampa workshop. This project is started on French national project, and finally we had we are lucky to have more participants. So I'd like to thank also all participants. So you already see the neodymium. Thank you for the previous speaker, so I can skip some explanation. So this map just shows the part of the result of the NeoSampa database. Ipsoneodymium value, isotopic composition indicated with ipsoneodymium notation. The present day seawater deeper than 1,500 meters. So as you see, there's a clear gradient from North Atlantic towards the Pacific along the global submarine circulation. So this is why neodymium has been used successfully to reconstruct the past oceanic circulation. But still, we have several points to be clarified. External neodymium sources to the ocean is continental material. So close to the continent, we have influence of the local detrital neodymium inputs. In the open ocean condition, seawater ipsoneodymium value can be determined by the relative contribution influence of water mass mixing, characterized by different ipsoneodymium value, and also vertical neodymium transport via reversible scavenging. So to further improve application of neodymium isotopes to reconstruct past circulation, we need to identify areas strongly affected by local regional neodymium inputs, and also we need to evaluate faithfulness of ipsoneodymium recorded by various archives. So our approach is to construct new neodymium isotope database, not only for seawater, but also archives younger than 10 kilo year. And the original part of this new database is integration of temperature, salinity, oxygen, nutrient, carbon-14, delta C13, and also distance from margin. So this slide shows the spatial distribution of compiled data. So black dot indicates seawater location. And as archives, we considered foraminifera tests, deep sea corals, fish teeth and debris, and various leachate. So the distribution is quite heterogeneous, and we don't have systematically the ipsoneodymium data, both seawater and archive. So this is a difficulty, additional difficulty to make comparison to evaluate faithfulness. And two lower panel indicate histogram of the data as a function of the depth. Seawater data number is almost double of the archive data, thanks for GeoTraces program, and we have a lot of data coming from surface layer. Indeed, the surface layer is very interesting because we see very clearly the influence of the external sources. So this depth profile shows neodymium concentration in the upper panel, ipsoneodymium values in the lower panel, and the color code indicate latitude. So warmer color indicates northern hemisphere, cooler color indicates southern hemisphere. So as you see, the very high concentration appears at the surface layer, and the ipsoneodymium range is quite huge. It's confirmed the main external sources enter from the surface of the ocean. It's very fascinating, very exciting, but because of the limited time for this presentation, I focus on the deeper layer, deeper than 1,500 meters. So the conventional idea of the evolution of seawater ipsoneodymium value during thermohaline circulation is a mixing between low ipsoneodymium North Atlantic water mixed with more radiogenic Pacific water. So upper three panels indicate the mixing, the ipsoneodymium value of the deep water as a function of silicate, phosphate, and the reverse of the concentration. Different colors indicate different oceanic basins. So this conventional idea is quite fit the available data. But if you see the detail, a lower panel, this time the color code is latitude once again. Very high ipsoneodymium value occurs also in equatorial Pacific. And also, what is interesting is very high ipsoneodymium equatorial water is concentration is quite depleted. So there's an add of radiogenic neodymium, but the concentration doesn't increase. And another part, interesting, so indicated with these figures, ipsoneodymium, the reverse of the concentration doesn't form a mixing envelope, so neodymium concentration has non-conservative behavior. So this is a global trend. Now I will show you the more detail. Just to take an example of Pacific Basin. So in this figure, Epsilon neodymium of Pacific seawater is plotted as a function of temperature, salinity, carbon-14 delta C13, silicate, phosphate, and dissolved oxygen. And to comparison, I put also the relationship between silicate and phosphate. Again, the color code shows latitude. So we thought Pacific, there are a lot of contribution of radiogenic neodymium coming from the continental margin, but surprisingly that this mixing between southern component water, northern component water is clearly indicated. But we observe some exceptions, some sites out from the general trend, some data coming from the continental margin. I'm sorry, it's not very clear. But this mixing, this multi-property plot shows the majority of epsilon neodymium variation can be explained by the water mass mixing. And also, this mixing envelope we can use to deduce the comparison between seawater and archives. So this is a comparison. Gray dot indicates seawater value, and the colored symbols indicate different type of archives. So generally, we observe a quite nice agreement between seawater and archives. But archive data tends to be plotted in the upper limit of the seawater. So using this multi-scatter plot, we can deduce some sites out of the general trend. But this is visual identification. It's not enough robust. So how we can quantitatively estimate offset of epsilon neodymium, which can be related local detrital neodymium inputs. Remember that we had quite nice correlation with hydrography parameters. So we established empirical equations that predict, so that the very similar approach to the previous speaker, predicted the epsilon neodymium values using multi-regression analysis. And then we assume that the large offset from the predicted value indicate local or regional neodymium detrital inputs. So this is the relationship between predicted and observed epsilon neodymium value. It's quite nice agreement. And this is the histogram of the difference between observed and predicted value. So in our case, when the difference is more than 2 epsilon unit, it's out of the 2 sigma. So we interpreted, we have input of radiogenic neodymium, and when the difference is less than -2 unradiogenic neodymium contribution. So this is a comparison between predicted and observed seawater epsilon neodymium value. Color dot indicate the observation, and the colored background is predicted value. In the case of Atlantic, in the case of the Pacific, and the equation established is indicated here. So we observe quite nice gradient, latitudinal gradient with predicted value, and using this relationship, we identified, we determined the distribution of sites affected by local or regional neodymium inputs. So color code indicate positive offset, and the cooler color indicate negative offset, so unradiogenic neodymium contribution. And lower panel indicates the site distribution relationship between distance from margin and water depth. So as you see, the majority of the case, the local effect occurred within the 1,000 kilometer. But it's not systematic. Some sites very close to the continent doesn't show local effect. So it's not really simple. So this is seawater case, and this is the archive case. We observe some similarity, radiogenic offset, equatorial Pacific, close to the Iceland, and close to the Hawaii, unradiogenic offset Bay of Bengal, probably the contribution of river particles. And another point we observe is in the archive case, more positive offset is more frequent. We can explain this trend by 2 ways. The first one is probably we artificially dissolved radiogenic material, volcanogenic material, when we extract oceanic neodymium, or pure water is already influenced by radiogenic neodymium. And is there any trend with alkali type? And the answer is no. So this figure shows alkali types. You see the various colors. It means some sites, when it doesn't work, it's not type of archive. So the offset is rather related to the location. So I emphasize the case it doesn't work, but remember the majority of the case, neodymium work quite well as a water mass tracer. So the final figure is I plotted neodymium value of the seawater deeper than 600 meters as a function of latitude, as a case of the Atlantic, in the case of the Pacific, and this time color code shows the water depth. As you see, we observe a quite nice latitudinal trend. In the case of the Pacific, it's a bit complicated because of the existence of this equatorial Pacific intermediate water, which has very high neodymium value. And this trend is also preserved in the archives, except some sites. So the conclusion is, I think we have two news. Good news is neodymium works quite well. We can deduce the northern component and the southern component water. And we provide some idea, for example, 1,000 kilometer could be a new constraint for the future neodymium modeling studies. And the bad news is still we don't know why some sites, the territorial influence is more significant, and some sites we don't see. So we need more study. Thank you for your attention.
Do you think we need more kind of incubation studies like the Pierce study where different sediments are tested for their exchange with seawater? To understand that?
Incubation study is one way, but I don't think this is only the way. Maybe we need some sites, some targeted site. And my personal feeling is stock of the particle is very important. Stock of the particle, yes. So maybe we can do already something to just make comparison the concentration of the particles of some targeted sites.
Number three.
Number three.
Number three here. No, I mean in your conclusions. Okay.
Number three at the conclusion.
1,000 kilometers away.
Yes.
What about, if you go in the past, what about intervals when there was a large spreading of material from one source throughout most of the northern Atlantic? Would you enlarge your boundary?
Well, I don't know the meaning of 1,000 kilometers. When I think Bob asked me the previous Congress, and is it diffusion? I don't know. This is just compilation. So maybe, I think probably this empirical distance is just related several different processes. So,
under present boundary conditions.
Yes.
Thanks for the invitation. I have changed my title a bit. The new title is Extracting Acid Exchange Component CO2 using carbonate and nutrient proxies and its application to the glacial North Atlantic Ocean. So first of all, this slide shows surface PCO2 for the pre-industrial period. This white curve shows 280 ppm value, which is the atmospheric PCO2 value for pre-industrial time. As we can see, for the North Atlantic Ocean, the surface PCO2 was lower than 280 ppm. Therefore, this region was a sink of CO2. We would expect some CO2 invasion from the atmosphere into the ocean. However, the absorbed CO2 is not easily seen from dissolved inorganic carbon because, this is not surprising, because DRC, in addition to acid exchange, is further affected by biological processes. This is demonstrated by strong similarities between DRC and phosphate in the Atlantic Ocean. We followed the approach from Brooker and Bern to calculate a tracer called DICAS to reflect acid exchange component CO2 changes. The equation we use is this one. It accounts for salinity effect and biological effect, including soft tissue and hard part calcium carbonate effects. So after the corrections, the DRCAS distribution for the pre-industrial Atlantic Ocean looked like this. North-like deep water had higher DRCAS, while the southern source waters, including Antarctic intermediate water and Antarctic bottom water, had low DRCAS. So this is consistent with CO2 uptake in the North Atlantic Ocean and CO2 outgassing in the Southern Ocean. This is already known and not that surprising. However, for panel applications, DRCAS is not that straightforward because we do not have a DRC proxy for panel studies yet. So a roundabout is to use a linked CO2 variable. Here we use carbonate. Just as a rule of thumb, in seawater, DRC and carbonate are inversely correlated. We calculate a new tracer called carbonate AS to reflect acid exchange component CO2. This shows carbonate calculated using DRCAS mean ocean alkalinity at a constant temperature, salinity, and pressure. As you can see, NADW has a lower carbonate AS, while the southern sourced waters have higher carbonate AS values. You may already noticed DRCAS and carbonate AS are inversely correlated. Our data show a slope around 0.6. So in essence, carbonate AS reflect the carbonate variations at a constant physical and biological condition. To reveal the acid exchange component CO2 changes, we can use this cross plot between carbonate and phosphate. When normalized to the same temperature, salinity, and pressure, carbonate is mainly affected by two factors. One is the so-called biological process, which affects carbonate and phosphate along the biological Redfield slope. The second factor is acid exchange. It only affects carbonate without any effect on phosphate. CO2 invasion would decrease carbonate, while CO2 outgassing will raise carbonate in seawater. For surface waters from the North Atlantic Ocean, we can see from Gulf Stream to polar North Atlantic Ocean, the data plot along a steeper array than the biological trend. This is consistent with CO2 uptake in the North Atlantic Ocean. If there were no acid exchange, we would expect to see this trend when phosphate is increasing during the northward transportation of Gulf Stream surface waters. If we compare this hypothetical point with the observed NADW value at a constant phosphate value, then we see a gradient at about 30 micron. This gradient reflects the carbonate AS gradient between Gulf Stream and NADW. It reflects a net CO2 uptake by the North Atlantic Ocean for the pre-industrial period. We suggest the carbonate AS gradient between Gulf Stream and the North Atlantic deep water can be used to reflect the CO2 uptake intensity by the North Atlantic Ocean. From Gulf Stream to polar North Atlantic Ocean, then to the North Atlantic Ocean, the carbonate AS decreased by 30 micron for the pre-industrial period. This reflects a DRC increase by about 50, if you remember the slope at 0.6. What does that mean? It means for each kilogram deep water formed in the North Atlantic Ocean, about 50 micromole atmospheric CO2 will be absorbed by the North Atlantic Ocean for this pre-industrial period. For pan-EU applications, our aim is to investigate the North Atlantic Ocean CO2 uptake intensity changes between Holocene and LGM. To this end, we want to reconstruct surface and deepwater carbonate gradient normalized to the same physical and biological conditions. We use ODP 999 from Caribbean Sea to track the Gulf Stream surface water signals, and we use both 7K from the polar North Atlantic Ocean around 1 kilometer depth to track North component deepwater signals in the past. Here is data for ODP-99 surface water. Surface carbonate were reconstructed using G-boron isotopes. For surface nutrient, we assume the nutrient remained at zero in the past due to its oligotrophic setting of this site. For deep waters, carbonate at both 7K was reconstructed using two methods, benthic boron Cas ratio and benthic boron isotopes. These two methods give consistent results in terms of carbonate. For deep water nutrients, including cadmium and phosphate, it's based on benthic cadmium to Cas ratios. As we can see, compared to the Holocene, due to the LGM, the deepwater nutrient at this site was lower. This is consistent with previous study by Marketo and Broca. Compared to AADW, glacial North Atlantic intermediate water had lower nutrients. Of course, there were other studies suggesting the same conclusion regarding the nutrient change for the North Atlantic intermediate water. Now, if we plot up the in situ carbonate and phosphate values for the surface and deep waters on this cross plot, it will look like this. These are in situ values. Therefore, they are not directly comparable if you want to extract the CO2 acid exchange component changes. Especially if you consider temperature and nutrient levels between surface and deep waters, they are quite different. So what we do is to correct temperature salinity pressure effect for ODP-99 carbonate. This will decrease the value by about 30 micro. The next thing we do is to further add nutrient increase, and this will decrease carbonate and increase phosphate along this biological trend. So by this point, the carbonate for the surface and deep waters are compared at the same physical and biological conditions. At this point, the gradient is about 35 macro for the Holocene. We can do the same practice for the LGM. Here shows the in situ composition for the surface and deep waters. They are quite different. Again, we need to make some corrections. First correction is temperature, salinity, and pressure. This is so-called physical correction. That will decrease the surface carbonate. The next thing we do is correct for the nutrient changes. Okay, basically put the surface nutrient at the same level as the deep waters. So by this point, again, they are compared at the same physical and biological conditions. The gradient was about 100 micromole for LGM. So compared to the Holocene, the gradient increased for the, okay. So this gradient change between Holocene and LGM is highly reproducible based on several cores from the polar North Atlantic Ocean. So if we combine the data for all the cores together, we can see the gradient for the surface and deep water between the two time slices will be 65, with the LGM having a high gradient. So we attribute this increased gradient to more efficient CO2 uptake by the glacial North Atlantic Ocean. So how to achieve this enhanced CO2 uptake during the glacial? Let's look at the Holocene first. For the Holocene, we know that the CO2 uptake by the North Atlantic Ocean is due to fairly strong solubility and biological pumps. The solubility pump is due to the cooling of surface waters during the northward transportation of Gulf Stream surface waters. And if we compare to the Southern Ocean's nutrient values, in the North Atlantic Ocean, the subpolar and polar regions, the surface nutrient is much lower, but it's not zero. If we look at the cooling for the glacial North Atlantic Ocean, we see a stronger meridional cooling from the low latitude to the high latitude in the North Atlantic Ocean by about 5 to 8 degrees C. So this cooling is much greater than the global mean. This is supported by both proxy and model result. This suggests a stronger solubility pump for the glacial North Atlantic Ocean. Regarding biological pump, we think during the glacial period, it was more efficient as supported by surface nutrient reconstructions and nitrogen isotopes. Okay. So compared to the Holocene, during the LGM, both solubility and biological pumps were enhanced. For the LGM, we know the climate would be windier, which would facilitate acid exchange, and that would enhance CO2 uptake by the glacial North Atlantic Ocean. Our data also afford a first estimate of CO2 sequestration by the glacial North Atlantic Ocean. I know, but I will be finished very soon. Okay. Compared to the Holocene, the gradient was increased by 65, as indicated by our data. That means DRC increase will be about 110 micromole. What that means is that for each kilogram of deep water formed in the North Atlantic Ocean, glacial North Atlantic intermediate water would absorb 110 more extra CO2 compared to NADW. If we make assumption of NADW occupation of 50% in the Holocene, in the global deep ocean, and if we assume 30% occupation of glacial North Atlantic deep water in the deep ocean for the LGM, then the total amount of CO2 absorbed by the glacial North Atlantic Ocean will be 250 gigaton extra, okay? It's important to note that this amount of carbon is due to acid exchange component CO2, okay? So it's very relevant to atmospheric CO2 changes. I'm running out of time, but I'm finishing, okay? If you look at the inventory changes of different carbon reservoirs, it's quite straightforward to conclude that enhanced CO2 uptake in the LGM North Atlantic Ocean was large enough to account for a significant portion of the carbon lost from the atmosphere and the land biosphere. With that, I thank you for your patience.
Good afternoon, everyone. I want to start with two major findings from the 80s. So imagine where we would be in the Paleocean sciences without these findings, right? So Jean-Claude Duplessis in '84 suggested or found out that the carbon isotope ratio of CBCides or CBCdoides directly reflects that of dissolved inorganic carbon broadly in a one-to-one manner. And then Lutze and Thiel in '89 found out that CBCides Willisdorfi is especially suitable to reconstruct C13 of seawater because it prefers an elevated position above the sediment-water interface. And that's especially the reason why we all love Willisdorfi so much. But a lot more data is available now to assess the consistency between seawater C13 and epibenthic C13. And that's exactly what this large group within the OC3 framework has embarked on to do. So OC3 is a international working group of pages, and the broader goal is to reconstruct ocean circulation and parsed carbon cycle dynamics. And you will find me talking a lot about we and us, but in fact it's Andreas Schmidtner who has led this study, and I'm simply the messenger. We have collected about 1,700 new or published and unpublished epibenthic C13 data. So all these dots you see here, most of this is published. So for instance, the black stuff is from Carly Peterson's 2014 compilation. And then the green and the orange is from Andreas Mackensen, also published data. But then a lot of the co-authors have shipped in new unpublished data here from off New Zealand, Helen Bostock, from the Pacific, Alan Mix, from the Atlantic, Janne Repschläger, Elisabeth Michel, and so on and so forth. We have also updated the seawater C13 database. This is mostly VOC data, geosex data, geotraces data, and so on and so forth, and even more databases. But you already see that the seawater C13 data and the epibenthic C13 data are not co-located. So what do you do? So Andreas has decided or has established a certain criteria to map the seawater data onto the core sites. So what he has done is he has used a liberal criteria, which is using a radius of 1,000 kilometers around the core data to map all of the data that falls within this radius onto the core site with equal weighting. So it's simply a regional average. But this, of course, comes with some uncertainties. So the mapped seawater data does not necessarily need to represent the true seawater data at the core site. And you see that the variance of the mapped data is particularly high in the polar regions, but overall the error is, or the variance is rather small in comparison to the disequilibrium between seawater and epibenthic C13. So we think, or Andreas thinks, that the contribution of the mapping uncertainty is relatively low. Another issue addresses the age determination. So you see we have collected mostly late Holocene data, so combining many measurements. The age is mostly based on radiocarbon and benthic O18 stratigraphy. But what we have also done is we have included data that were measured on living foraminifera, so rose Bengal stained foraminifera. This is basically mostly Andreas Mackensen's data from multi-cores or box cores. And then we've also taken the upper 10 centimeters of some cores where age model was not that great, but this was again checked with benthic O18. My favorite issue is, another problem is species information. So most of the data didn't come with species information, and if you know all the names or all the species of these pictures here, that's really great. But in fact, the species, to really unravel the species or identify the species is relatively difficult and often subjective. So this might be one reason why the species were combined as PP in the database, and was maybe also often missing. So 25% of the data in the database had species information. The last one concerns the Süß effect. So Andreas was consulting former model simulations, and he was deriving a time-dependent Süß effect and was correcting the seawater data and Andreas Mackensen's data on the living foraminifera. And you see that the Süß effect, of course, was strongest in the North Atlantic. All right. Let's have a look at the data. So you see the foram data, Süß effect corrected, and the seawater data, Süß effect corrected as well. And it comes not as a surprise that the North Atlantic is relatively enriched and the Indian Ocean and Pacific is relatively depleted in C13. And an important and interesting feature that Andreas pointed out in his study is a relatively low C13 belt here running from the Drake Passage to the northwest, sandwiched between the North Atlantic rich C13 and Weddell Sea C13. Let's have a look at the difference. So the difference, you see that the difference is particularly high, or So the forum is, what is it? So, I mean, there's a positive bias in the so in the Arctic Ocean and in the Antarctic. And this, in particular, we think is related to thermodynamic fractionation during air-sea gas exchange at low temperatures. So this is how the data looks like. Here also a depth transect in the Atlantic and in the Pacific and in the Indian Ocean. And you see that the minimum that I was pointing out more or less is affecting the whole water column, and similarly the positive biases as well. Yeah. So, and if you take the standard deviation of the difference of these data here, we end up with 0.33 per mil, and this you could take as an error estimate of the one-to-one relationship of C13 versus seawater C13. All right, how can we better predict seawater C13 based on CBCDIS data? So Andreas has done a huge amount of sensitivity studies, and his first one was just to simply assume, all right, I simply try to test whether B must be 1 at all times. And what he comes up with a few sensitivity studies here, so this is a regression through all the data. He comes up that B is always lower than 1. If he also included carbonate ion as another factor, he came up with a significant slope. So if he takes the difference between the SIP and the seawater data, he comes up that the residual can be explained to some extent by variations in carbonate ion. And it's interesting that, so here in this line here is actually the planktonic foraminifera so the carbonate ion, so the extent to what planktonic foraminifera are influenced by carbonate ion concentrations. So this was done based on Howard Sparrow's work, based on cultural experiments. So it seems to be similar. He also included the depth as one factor or component influencing benthic C13, and again the residual seems to be consistent, or the slope seems to be significant. And it's also similar to this, there's a light green line here. It seems to be similar to reaction diffusion models by Tillman-Hesse here. All right, so the key message is here that we can decrease the uncertainties of predicting seawater C13 by including all these other components. Just a quick look at species information. Here again, in green, Villersdorfi, Kullenbergi, Lobatulus, and Pachyderma. And as I said, most of the data are based on Villersdorfi. And as you see here in these numbers, the arrow seems to be in, that's one particular sensitivity study, the arrow seems to be smallest for Villersdorfi. For Pachyderma, there's not a lot of data available to make a reliable statement. But again, Villersdorfi seems to be most robust, if you want to say that. And then a last look at different regions. Let's start with the Arctic. Here you see a depth transect. So the black data is actual seawater data, SÜSS-effect corrected. And then the red one is the forum data, also SÜSS-effect corrected. And the green one is the predicted data based on Andreas' regression. And you see that there's mostly a positive bias. So that's probably due to air-sea gas exchange at low temperatures. The second one is the South Pacific, so this area here. And you see that the fit is actually quite nice. Yeah? And then the last one, Arctic, Antarctic, and Southeast Atlantic. You see that in the Southeast Atlantic, we have mostly a negative bias, and the bias is relatively strong. In the Antarctic, we have both a positive bias and a negative bias, and that's quite substantial. So I recommend, if you have a favorite study area, that you would check out these regional analysis in this new paper by Andreas Schmidtner to see already the modern biases in the SIP data, and then to maybe improve your reconstructions in the past. All right, just a quick conclusion. So Andreas showed significant carbonate ion and pressure effects on epibenthic C13. So this is probably the first indirect evidence for a carbonate ion effect on benthic C13. For planktonic, it has been showed quite nicely already. And the calibration removes some systematic biases in comparison to the one-to-one relationship, and the regression is still, the error is still 0.52 per mil, which is higher than the Duplessis estimate of 0.15, but it's larger in the South Atlantic, and it's larger for species other than our favorite Cibicides willersdorfi. Thank you very much. And, sorry, check out, please, this paper. It's in press now. Thank you.
I've seen a recent talk by Samar Katiwala where he actually showed modeling results for the last glacial that were like a per mil off for deep delta C13. Do you think that that what you're observing here may explain part of that, of those offsets?
Yeah, so what was the reason that he gave for this mismatch in his model simulations?
He couldn't say.
Okay, he couldn't say. So I personally think that a lot of this issue might have something to do with seasonal effects as well, and also possibly microhabitat effects of particular foraminifera.
In the end, it might be good news for him because we thought his model is wrong, right?
Okay.
Could you expand a little bit on the Arctic story and how you explain this offset?
So yeah, maybe I haven't. I was too fast at that point.
You mentioned a gas exchange at low temperature. I'm curious too.
So this data is mostly Andreas Mackensen data. So this is box cores and multicores. So the forums were living at that time, and they were possibly only recording a brief snapshot of time, basically. So this is different from having a late Holocene mean. So this could be one of the reasons why this is more positive. But then in this paper, he also makes the argument that it has something to do with air-sea gas exchange at low temperatures. Yeah, exactly.
Thanks very much for being here and for the invitation. I really appreciate having this forum to present this research. And yeah, it's my first Pages meeting, so I'm really excited to learn a lot this week. So what I'm going to talk to you about today is I'm basically going to hopefully convince you that we can use the isotopic composition of cadmium in deep-sea corals to back out vital effects in these organisms to actually reconstruct meaningful cadmium-calcium measurements within them, which hopefully will tell us about the distribution of cadmium in the water column. And as Catherine pointed out this morning, our motivation for doing so is that we know that the distribution of some of these traces in the ocean, this here I'm showing the phosphate distribution from the Dutch Geotraces expedition. We can see these are the sort of canonical nutrient type distributions in the ocean. And we know that they're impacted by a combination of biological, physical, as well as ecological processes that set these distributions. And so it stands to reason that should we be able to reconstruct this distribution in Earth's past, we would also learn a lot about all of these processes for times in Earth's past as well. And so there's a lot of merit to trying to understand these distributions through time. I'm going to say something a little bit controversial maybe, but that is that I think by and large the ocean interior is still relatively poorly served by nutrient proxies. And by that I specifically mean the nutrient proxies that record ambient nutrient conditions in the deep ocean, and specifically not those that are recording what's been exported from the surface. And whilst I think the situation has changed a lot potentially in the last 5 years, we're still not anywhere near the level of resolution that we have in the surface ocean. So what can be done about it? So you may not have noticed just then, but I've switched from phosphate to cadmium distributions measured along that same section in the Western Atlantic. And what we can see is that the distribution of the two elements, this is cadmium now in nanomoles per kilogram, is remarkably similar. And I'm not going to get bogged down into the argument today about why they look similar, but we'll just say for now that they exhibit a degree of similarity. And so the reason we might care about cadmium, knowing that it looks like phosphate, is that cadmium actually readily substitutes for calcium in marine carbonates, right? We know it definitely goes into the lattice. And so that's this point about here. We can argue about that after the talk if you want. And so if we are able to reconstruct cadmium-calcium ratios in deep-sea corals, noting that they live within the ocean interior on seamounts and such like, that we would potentially be able to reconstruct this distribution through time. Now, I'm not the first person to have thought of this. In fact, one of my co-authors, Jess Adkins, did a similar thing in the late 90s. He measured a deep-sea coral specimen from here in the North Atlantic. And what he found was that as you go along the growth axis of an individual septum of this deep-sea coral, they see large enrichments in cadmium-calcium along the growth axis of the coral, and that this is bracketed by radiocarbon measurements. And they interpreted this shift as evidencing a very large increase or a large change in ventilation of the deep North Atlantic approximately 15,000 years ago. The problem with this interpretation, unfortunately, and I've run this by Jess, is that most corals show this enrichment. And so here are some modern corals recovered from very similar localities, and we note that they record very different cadmium-calcium ratios. In fact, this one's almost an order of magnitude higher. And we notice that they both show increases. This increase may occur somewhat linearly along the transect, or it may occur as a step function. But it seems to occur even regardless of the starting value as well. So it becomes difficult to interpret patterns such as this in terms of changes in deep ocean ventilation when all the corals show this same pattern. And so the question then becomes, well, which corals can we trust if we don't have a reliable means to back out the vital effects? And that's what we're interpreting this signal as, particularly in the modern corals, that this must be a vital effect. And so that's where I'm going to pivot to cadmium-stable isotopes. So why might we be interested in this proxy? Well, cadmium-stable isotopes, like any isotope system, are very good at tracing mineral fluid reactions and potentially backing out the conditions under which reactions took place. So in this case, we're thinking about biomineralization. And so cadmium-stable isotopes, like any other isotope system, we measure them in the delta notation, heavy over light, sample over standard in per mil. In this case, our standard is this NIST SRM ICP-MS solution. And so if we go out and we measure a suite of deep-sea corals, what we find is there's actually quite a large range of cadmium isotopic variation. So here we've got almost a per mil of variation and 2 orders of magnitude of variation in the cadmium-calcium. But as you may remember from one of the first slides, in order to interpret this variation in terms of whether or not it's water column or whether or not it's all just signals, relics of biomineralization, we need to know 2 things. And the first thing that we need to know is the cadmium concentration and the cadmium-stable isotopic composition of the waters in which each one of these corals grew. Well, that's the first thing I'm going to touch on. So up until geotraces, this was a compilation, that's what I'm looking for, a compilation of cadmium and co-located cadmium and phosphate measurements put together in this review article that I was a part of in 2011, showing that this was our view of the cadmium-phosphate relationship in the ocean, showing that there seems to be a pretty broad trend, but there's a reasonable amount of scatter on it. To plug the recent geotraces intermediate data product and to point out that all of these sections are available on egeotraces.org, by adding in all of this recent geotraces data, this scatter plot has now been significantly infilled with all the recent data. And we can see that maybe a lot of that original scatter may have just been analytical, and that actually the cadmium-phosphate relationship is very tight. But as pointed out by one of the questions earlier, it is certainly not linear. I won't touch on the cadmium isotope composition of the water in which the corals grew, but by and large the deep ocean shows much less variation than the surface ocean, and we can talk about that afterwards if you're really interested in that. But we do factor in there is a little bit of variation in there, but not much. Certainly not a per mil. So because of geotraces now, we've exploited that data, we've put it to use to hopefully find out what the, how much of this variation is due to the water column. But the second thing that we need to know in order to fully interpret this is the elemental and isotopic partition coefficients for cadmium into calcium carbonate. And the reason why we might want to know that is because then we can interpret this variation in terms of just being relics of precipitation artifacts, or whether or not it's maybe contamination or some other process that we're not considering. So it's worth pointing out here that cadmium likes to be in calcium carbonate a lot. In fact, it's a much better fit in calcium carbonate than calcium. And so here's some pretty seminal paper from the 90s by Tesoriero and Pankau. And what they showed was across 8 orders of magnitude in precipitation rate, the partition coefficient for cadmium into calcium carbonate is anywhere between about 200 and 3,500. So the partition coefficient, just for those of you that are unfamiliar with this, is just the ratio of cadmium to calcium in the solid relative to that in the liquid. And we can see that cadmium under all conditions is dramatically enriched in the solid relative to the liquid. So whilst we might not know the exact partition coefficient for the corals that we're looking at, I think it's safe to say that it's probably greater than 1, possibly even a lot greater than 1. So what about the isotopes? Well, thankfully, I finally get to put this paper that I published in 2011 to good use, because we actually did some inorganic precipitation experiments where we tried to mimic the range of conditions that Tesoriero and Pankau used in the 1990s. And what we found was across a wide range of these partition coefficients that we basically always observed a fixed isotopic offset of about 0.995. Now, there's a lot of scattering there, and some of that's due to the fact that some of these offsets were measured from the precipitates and some from the residual liquid, and so there's a bit of error magnification there. But anyway, the main message is that pretty much regardless of the partition coefficient, temperature, magnesium, you name it, we always get the same isotopic offset of this 0.995. And so this, oh, there we go, that's not what that's meant to be. This is meant to be an alpha. For those of you, again, not familiar with the notation, the alpha is, you can think of it as effectively a partition coefficient, but for isotopes. So in this case, it's the 114/110 ratio in the carbonate relative to that in the dissolved phase. And so to put that in delta notation, that's equivalent to an offset of about 0.5 per mil in our notation. Okay, so now back to the corals. So this is the map showing all the samples that we analyzed. There's 17 in total. Most of them are these Desmophyllum dianthus, but we had a couple of other ones in there as well. And what you see is there's a very clear trend in the dissolved cadmium concentrations, or these are estimated from the World Ocean Atlas gridded phosphate data. We can see a very systematic increase from the North Atlantic to the North Pacific in cadmium concentrations. So we know that some of that scatter on the x-axis is actually due to the fact that these corals lived in very different water masses. The range of depths that we looked at was between 750 to about 2,200 meters, but there's really nothing, there's not that many desmophyllums below that. And so now what I'm doing is I'm showing the cadmium-calcium elemental data for our corals here on the y-axis, plotted against the cadmium-calcium ratio of the water in which they grew on the x-axis. And you can see this is a log scale, so there's actually quite a lot of variability. But I think the main thing to take from this figure is that basically all the corals fall above the 1-to-1 line. So in this case, we only have a couple of specimens that actually seem to record ambient seawater with no offsets. That would be anything that's exactly on this line. Interestingly, this one is not actually a coral, but the holdfast that a coral had formed as it was clinging to a basalt substrate, and that apparently recorded the water with no offset, so that's maybe interesting. And the other thing to point out is these grey bars correspond to where we analysed different septa from the same specimen to see if they gave the same systematic offsets from the same individual but different parts of it, and they seem to reproduce quite well. And the Y error bars, I should say, is actually not reflecting our inability to measure this precisely. Our actual precision is probably about the width of my laser pointer. Most of this variation is actually within the individual coral specimens. A lot of them show pretty significant enrichments as you go along the length. So what about the isotopes? So now what I'm going to do is renormalize all this concentration data to the ambient concentration. So anything that's on the line is going to have a partition coefficient, a KD of 1, and anything above it is going to be positive. And what we see is when we perform that normalization, all the corals fall between about 1 and 15 at the high end. I've also performed here an isotopic normalization, so I've subtracted the ambient water column composition from the corals, so that corals that mimic ambient seawater with no isotopic offsets plot here along this 0 per mil. This is now in big delta, cap delta space. And what we see is that the corals pretty much fall into two distinct populations. The first population up here seems to record seawater with basically no isotopic or elemental offsets, so they're pretty much recording ambient seawater. And then we have this second group of corals down here that seem to be substantially or significantly enriched in cadmium that also exhibit about a 0.5 per mil offset. And for those of you who remember my 2011 paper, there it is. There's our inorganic offset, and it's actually, thank you. It's actually pretty satisfying to see that they plot within a similar domain. The problem with this, though, is that though we can explain these corals, it's kind of difficult to explain these corals up here because we don't have a common mechanism for linking these two together. And that's where I'm going to introduce this calcification efficiency model, because I think this is a really important and really powerful means to explain how we can go from looking at skeletal aragonites, which is obviously what we have in the depositional record, and going back to the seawater concentrate or composition, which is actually what we care about in most cases. And we can actually envisage models such as this as a simple Rayleigh-type batch reactor if we just imagine that each of these fluxes that's tapped into our calcifying fluid has a valve associated with each one. And we can envisage this for any ion that's being transported into this calcifying fluid. The balance between the flow through and the rate of precipitation sets the calcification efficiency. So if the rate of flow through vastly exceeds the rate of precipitation, we're going to end up with... I'll get to that on this next slide, actually. Okay, so anyway, that's the calcification efficiency model. And if we want to be able to relate this back to the seawater composition, which is the thing we really care about, we either need to assume that this calcification efficiency, or F, is known, that we have some way of calculating it, or that it's constant through time. So we can fit a Rayleigh model or this calcification efficiency model to our data, and what we can see is these corals down here with the very high cadmium enrichments and the isotopic offsets would be consistent with corals where the seawater flow through is much faster than the rate of precipitation. Similarly, if we follow this F, this calcification efficiency, and we follow it all the way up to here to 0, we can get to corals that have no net isotopic offset or elemental offset from seawater. So that would be equivalent to basically where every cadmium ion that enters from seawater is deposited in the skeleton. Okay, so that's good. The real power of this model, aside from being a pretty figure, is that it actually enables us to link both the cadmium-calcium that we observe in the corals and the isotopes via a single process. And the power of that is that we now have an independent way of potentially getting back to this partition coefficient. So that is, if we were to pick up a fossil coral, measure its isotopic composition, we could hazard a pretty good guess as to what its partition coefficient was, read up off the graph, and then use that to back correct the cadmium-calcium. I will concede that we have not yet identified the control variable as to why some corals are down here and others are up here, but I have a few ideas, maybe crazy. So anyway, the quick question then, does it work? Well, to test that, we looked at some corals, again, from the New England seamounts that are currently bathed by cadmium-poor Labrador seawater. And to help orientate you with respect to time, here's the GRIP Delta 18O record, with some climate events marked on there. And what we see when we measure the cadmium-calcium ratio of these deep-sea corals, this is an age depth plot, we can see that the cadmium-calcium ranges from about 0.1 to 0.7 micromoles per mole, which is almost an order of magnitude higher than the cadmium-calcium in ambient Labrador seawater. So these corals, again, are showing very significant enrichments relative to the water in which they grew. We also measured the isotopic composition of cadmium in each of these corals, and again, we can see there's a pretty wide range of variation. Modern-day Labrador seawater, by this paper, another GeoTraces paper by Conway and John, showed that it's about 0.4 per mil. We can see the corals range from about -0.4 to 0.2, so again, they're all pretty fractionated. So if we perform our Rayleigh correction to back out the true cadmium-calcium, we can actually now start to make interpretations about the water column at that time. And so what I'm showing here is the reconstructed cadmium concentration in nanomoles for these samples, noting again the Labrador Sea is about 0.3. And what we can say, well, we can't say for certain that this is real, but it certainly is plausible, the numbers that we're getting out of here. Seeing potentially values of around 0.3 nanomoles in the depths coming up, approaching Antarctic intermediate water, that seems reasonable, and that would be consistent with the recent study published by Poggeman and others in EPSL. But then it also suggests that we have very, very, very low cadmium concentrations below 1,000 meters throughout much of the deglacial. I think that's kind of interesting. This is certainly a signal that's worth chasing down. So with that, I realize I'm very low on time. So I'll just take-home point. The one I really want to emphasize is I really think there's the potential to use cadmium isotopes to back out this vital effect and get back to the true cadmium-calcium of the water column. And that could be really, really powerful for reconstructing deep ocean nutrients through time. With that, leave up my acknowledgements and take any questions. Thanks very much.
You mentioned that you have some possibly crazy ideas for why the populations are so different. Could you tell us more about those ideas?
I think it's likely going to come down to probably one of three control variables: oxygen, food supply, so what's sinking through the water column, or possibly alkalinity. The problem is the calcification efficiency depends on two variables, right? It depends on both the growth rate and the seawater turnover rate. And because for these corals we haven't constrained either of those, we can only say where we are on the spectrum, but we can't relate it directly to one of those variables. But I think if you were to use, say, radium or something else to actually constrain the linear extension rate, you could actually then start to back out the control variables, and that might be really exciting.
So we're just beginning to understand the chemical oceanography of protactinium, and because of that, there's confusion on how to use it as a circulation tracer in the past. So I just want to talk about the modern chemical oceanography today. And what I'd like to tell you is that I think protactinium burial in the Pacific is explained by the location of these biogeographic provinces defined by Longhurst. In the Atlantic, I think these provinces will help a bit, but the takeaway message is that for protactinium transport at least, I think we should think of the Atlantic less like a bowling alley and more like a tennis court, and hopefully by the end you'll know what I mean by that. So, what is boundary scavenging? This theory was developed when the first protactinium-thorium ratios were becoming available in the sediments and some in the water column. And the idea here was talked about in the overview talk a bit. So these two nuclides, protactinium-231 and thorium-230, are produced homogeneously everywhere in the ocean by uranium decay at this constant initial ratio of 0.093. They're both very insoluble, and they adsorb onto sinking particles, and that's scavenging. Thorium is more insoluble than protactinium, so it gets scavenged on the order of decades, which means it can't be transported laterally very far, so it gets scavenged locally for the most part. Protactinium, on the other hand, is scavenged on the order of centuries, so currents and eddies can carry the protactinium away from areas of low scavenging intensity to areas of high scavenging intensity, which tend to occur near the margins where you have the highest particle flux. So in the sediments, generally, we find that protactinium-thorium ratios are below the production ratio in ocean interiors, where you have low particle flux. And at ocean margins, this is just a radial symmetry here. Ocean margins have excess ratios where more of the protactinium is actually getting buried there. So as part of my PhD work, I thought I'd try to test that idea with the greater distribution of surface sediments that were available at the time. So this is the map of the protactinium-thorium ratios. The production ratio is right about the green color. And so what I found through a series of multiple linear regressions is that the excess protactinium tends to get buried in areas with the highest export productivity, so that's the highest particle flux in the water column, and or high opal production. And biogenic opal tends to have a special affinity to bury protactinium. So these high deposition areas tend to coincide with these high productivity provinces that occur all along the Pacific margins, maybe a bit in the equatorial Pacific and in the Southern Ocean. Whereas the interior Pacific is very depleted. There's this large deficit all throughout the Pacific. And in fact, there's not a lot of east-west gradient in the Pacific, which you might expect if there's removal of protactinium by the overall advective pathway in the Pacific, which is the inflow of circumpolar deep water in the western Pacific. It really seems to fit this kind of bowl-shape analogy of losing protactinium in the interior going out to the margins. So to do a full protactinium budget to see if we're accounting for all the protactinium that's being produced, you've got to do some interpolation between the data points, and it's non-trivial to decide how to do that. But because of this grouping of protactinium excess in these high productivity provinces, I thought using the Longhurst provinces would be a good way to interpolate this map, and it makes it a little bit simple because you just do box averaging. And statistically, we actually did find less variation of the ratios within provinces than across provinces. So by just assigning each province the average protactinium-thorium ratio we find there and accounting for the water depth of the different provinces, I can actually calculate the protactinium flux throughout the whole Pacific in these provinces. And when I add up all the protactinium flux, we can account for something like 93% of the amount of protactinium that's produced throughout the whole Pacific. So we're doing a pretty good job of the ins and outs of protactinium. It gets produced the same everywhere, but it's preferentially buried in these high productivity provinces. So boundary scavenging really fits the model in Pacific. A couple decades after the conception of boundary scavenging of protactinium, people were looking at surface sediment distributions of protactinium-thorium in the Atlantic, and they found deficits, so less than production ratios in the interior Atlantic, and excesses in the Southern Ocean. But north of the Southern Ocean, they didn't find very many ratios that were in excess of the production ratio. So the thought was that, okay, well, the Atlantic is really more rapidly flushed than the Pacific. So this is the bowling alley idea, that you've got this pretty quick transport of water through the Atlantic. So perhaps protactinium just gets carried along with this flow, and the boundary scavenging effect, which would occur by eddy diffusion, can't operate as much. So it's dominated by this unilateral or unidirectional transport in the Atlantic. So to test that idea, I thought I'd go to what's available in protactinium thorium surface sediments now, which is much more than it was 20 years ago. And you can see here much of the interior Atlantic has a deficit in protactinium that's similar to the Pacific. The Southern Ocean is very enriched in the protactinium. But in the high productivity areas of the North Atlantic, you do see higher ratios, but they're not very much above the production ratio. And that's actually true in most of the margins around the North and South Atlantic, that you don't have a lot of excess ratios. So I thought to help understand how protactinium is moving, I thought I'd do the same Longhurst interpolation and add up all the protactinium flux to see where it's going. So that's what I've done here. And you can see the whole North and South interior Atlantic there's a large deficit here. There's increased ratios up in the far North Atlantic, but not above the production ratio. And really, you have the biggest excesses in the Southern Ocean. One interesting thing that stands out that the deficit in the South Atlantic is stronger than it is in the North Atlantic. So there's clear evidence for transport of protactinium from the South Atlantic to the Southern Ocean. But when I look at the amount of protactinium flux in the Southern Ocean, I actually need more than just the South Atlantic to explain how much is being buried there. So you do need transatlantic transport of protactinium from the subtropical North Atlantic down into the Southern Ocean. Another thing that was a little different, I didn't quite get to 100% of the total protactinium produced in the ocean, so there's a chance there's some areas we just haven't made observations yet that would explain some of that protactinium flux, perhaps some of these margins, maybe the Mid-Atlantic Ridge, but there's not really glaring evidence for a big missing sink of protactinium. But this is just what ends up in the sediment. So how exactly does it get transported in the water column? So the model that's been used and explained by Francois and others is that for both of these radionuclides, the nature of particle scavenging is such that you'd expect an increase in concentration with the linear relationship with depth in the absence of circulation effects. Once you have deep water ventilation, you would actually inject water that has lower radionuclide concentrations than is predicted by the scavenging equilibrium. So this results in excess desorption to try to get back to that linear profile. So there's a relaxation getting back to linearity. That relaxation would occur faster for thorium than it does for protactinium because thorium has a shorter residence time. So therefore, you'd expect increasing protactinium thorium ratios with water mass age as reflecting the transport of protactinium. So with the geotraces transects, we're starting to be able to test those ideas. So here's the Dutch geotraces section along the Western Atlantic, which we've seen a lot today. And in conservative tracers, it produces this nice reflection of North Atlantic deep water flow. This is salinity here. And in the protactinium, we do see this influence of ventilation, so lower concentrations being injected to depth. And as the water mass ages, it starts to get back towards something more linear as you go further south. We see the same effect for thorium-230, but when you do the ratio, you really don't predict what that model said of increasing protactinium-thorium ratios with water mass age, and it almost seems like the opposite. You have decreasing ratios. So the highest ratios in the water tend to be found in the higher productivity regions of the far North Atlantic and in the Southern Ocean. And it's like the whole tropical, subtropical Atlantic is deficient in protactinium. So this leads me to suggest an idea of how the protactinium is being transported. And it may be that the circulation in the Atlantic is much more diffuse than we tend to like to think about it. So Susan Lozier has been trying to emphasize this point with things like these model results where you release particles at the site of North Atlantic deep water formation. It's not like all of them go in an advective pipeline down the deep western boundary current. Some of them actually go north, some go quite far east, And in general, there's very circuitous pathways. So these eddies are kind of moving them around a lot, as the net transport may be in a kind of North Atlantic deepwater fashion. And this goes back to actually how Stommel first described what deep ocean circulation might have looked like. So he knew there would be density flows in the deep water, but he predicted that you would have gyre scale recirculations in each of the basins, and generally this would happen by eddy diffusion. So perhaps we have net protactinium transport along deep water flow, but the protactinium deficit gets homogenized somewhat by eddy diffusion in these gyre recirculations. So these would be the cross-court shots in a tennis game. So overall, I think you can get circulation information out of protactinium thorium distributions, but you really need to take a mapping approach, because there's no reason that these areas of deficit and excess protactinium should have remained the same under different conditions in the past. So you want to keep track of how much protactinium you're losing or gaining in the different regions of the Atlantic. And additionally, just in the modern system, we still need to describe how protactinium is getting transported. So I've got an idea of how that happens, but it's clearly very different than a conservative tracer. And so maybe for this problem, we can't use the nice two-dimensional advective bowling alley analogy of the Atlantic, but we've got to take into account the three-dimensional movement of the water. All right, thanks.
Very nice talk, Chris. I'm shocked. So how do we interpret the Bermuda Rise protactinium thorium record?
Well, yeah, I didn't want to get into that.
I know.
I don't have a dog in the fight of what happened during Heinrich Event 1, but yeah, it showed that there was less of a deficit in this region during that period. So it's hard to say what happened without knowing what happened in these other areas, which are the major sinks today. But yeah, at least there's evidence today that there's movement of protactinium from the North Atlantic all the way down to the Southern Ocean.
But the other course shows similarly high protactinium to thorium ratio. It's not only that one.
Yeah, I mean, people are starting to map this out, but I just think we need more than the number of cores. We can't really rely on a few cores.
I can potentially contribute to that question in the next talk.
Okay.
Pardon me for using a second laptop, because I'm heavily reliant on my presenter notes. So this is to ensure the smoothness of the talk. So, and a bit of a clarification. Actually, I'm currently working on silicon isotope now in the high latitude North Atlantic. But today, I'm going to present protactinium thorium findings from my PhD project. First of all, I would like to acknowledge my PhD supervisors, collaborators, and all my colleagues and groups that supported and provide assistance to this project. So I was originally going to start with a simplified cartoon of a school of thought on the protactinium, thorium in deep Atlantic. But Catherine and Chris Hayes has already done a good job in explaining the principle behind, so I'm going to skip that. So, if we follow the principle of the suggested a simplified relationship between protactinium thorium and North Atlantic deep water advection, in a scenario where the circulation rate is reduced, then we would expect less protactinium to be exported away relative to thorium, and then we should be able to see an increase in protactinium thorium in the sediment in the deep Atlantic. And this is supported by a number of ocean models. For example, there's a recent model by Ramford et al. They show a substantial increase in protactinium thorium ratio in the deep Atlantic if there's a collapse in Atlantic circulation and NDGW advection. So this is just a simulation, but it gives you the sense of how protactinium thorium could respond to changes in the Atlantic circulation. Following this, it could be consistent with previous interpretations of Jerry's record in Bermuda Rise, which suggests changes in circulation rate associated with millennial climate events during the last deglaciation. Nevertheless, there have been debates regarding the simplified relationship between protactinium and thorium Atlantic circulation rate. given other processes that could fractionate between the two isotopes and cause changes in the resulting sediment ratio. So just an example, the geotracer seawater analysis in the North Atlantic found notable elevations of seawater protactinium and thorium near margins, mid-Atlantic ridge, and identified nepheloid zones, which have been associated with additional scavenging processes in these regions. However, I believe that these findings are based only on seawater observations, and links to sedimentary distribution are crucial in examining the removal fluxes in those proposed settings of enhanced scavenging. And as of yet, there have been very few studies that I know that directly compare protactinium and thorium in both seawater and modern sediments. So this served as the motivation for me to analyze protactinium and thorium of paired core top sediment and seawater samples, which potentially contribute to further understanding the processes that influence modern distribution of these two isotopes. And this results I'm going to be presented in the next few slides. Then in the last part of the talk, I'm going to show a compilation of sediment records from the Atlantic Ocean, which some of the audience may be interested in, to assess the processes that control protactinium and thorium trends back in time. The paired core top and seawater samples analyzed were obtained during JC194 cruise, led by Laura Robinson in 2013. The samples were collected along 5 depth transects across the northern tropical Atlantic open ocean. The white field symbols are the sample seawater sites, most of which are in close proximity to the core top sites indicated by the star and the plus symbols. Next. Right, so results. The bottom plot show our seawater dissolved results and also existing data from the northern tropical Atlantic. Together, the compiled data set indicates a coherent decrease in seawater value with increasing depth, except at, let me try. Which one is the laser pointer? Sorry. Is it this guy? Oh, yeah, got it. Sorry. Not very good with techno. So, except at Beta seamount here. Ooh. Right, maybe I shouldn't try after all. Okay, you know where I'm talking about, the number 4. So there's a local elevation in protactinium and thorium between 2 to 4 kilometers at Beta. These sites also have low protactinium and thorium concentrations, indicative of additional scavenging processes. And when I compare these results with geotracer's North Atlantic depth section plotted above in the top plot, there are some apparent similar signature. For example, the low values in the deep water basin are consistent with net protactinium export away from the North Atlantic by NADW. So I agree with Chris Hayes that we need to have a more detailed dissect about how the latitudinal variation in protactinium thorium is reflecting the pathway of NADW. But for the purpose of this talk, I'm satisfied with saying that in overall it's showing net export by NADW. So the local elevation at Veda, depth transect number 4, is similar to those observed in hydrothermal setting and nepheloid zone identified in the geotracer section. But this remains a speculation here, as we did not find supporting evidence for the presence of hydrothermal band on nepheloid layer at deep Veda. So how about the core top sediment? Our core top results, indicated by the colored circles, which are superimposed on top of the seawater plot that I showed just now. I've also included some previously published core top data from the western margin. All sediment sites, all of them, below 2.5 kilometer, show values lower than the production ratio, again, reflecting net export by North Atlantic deep water, net protactinium export, which are consistent with previous studies, I think. In contrast, here's a new thing. Above 1.5 kilometer water depth, the core top protactinium thorium ratio are at or greater than production, with eastern and Bima sites, the eastern sites, having much higher values than the western sites. So to further evaluate potential scavenging processes that influence these sites, I've calculated the fractionation factor, the right plot, as defined by the equation there. It has been shown that variability in the fractionation factor of protactinium and thorium is related to particle composition. The range of values associated with a specific unmembered particle composition that I've also plotted there follow those derived by Chris Hayes in his 2015 paper and Chase et al. 2002. I'm not going to go through the detailed explanation to compare the fractionation factor and protactinium and the observed sediment ratio, given the limited amount of time I have. But in short, what this is showing is that the imputation that we arrive at, the combined fractionation factor value and the sediment ratio at the eastern site suggests enhanced scavenging of protactinium and an additional input of this isotope to the eastern MV sites and intermediate depths. This opens up further questions on the source of this additional protactinium and the main mode of transport of this isotope to these sites, which can be diffusion, lateral advection of intermediate water, or upwelling of deep water. This, I'm not sure, but this could be related to, linked to what Chris Hayes is presenting in the previous talk. It could be the missing protactinium burial, but it's hard to say because these are rare topography on its seamount, so I don't know how much of a percentage of the protactinium burial it can account in the modern day. Anyway, regardless, to summarize, our findings support the consensus that modern-day protactinium thorium signal in the deep basin is one that is dominated by North Atlantic deep water advection, while in the intermediate depths it's more interesting. It potentially reflects mixed scavenging and oceanic transport controls, at least in the tropical Atlantic. Right. So, what about the past? What are the main processes that control the trends of Atlantic protactinium thorium back in time? To investigate this, we have compiled all 23 of the available deep Atlantic sediment records that are relatively well resolved for the past 25,000 years when climate, ice sheets, ocean circulation, and marine productivity had experienced significant changes. The square symbols are the records that is generated in this study. What I'm not going to discuss here are the records shallower than 2.5 kilometer, because there are only 6 available records, which may not be sufficient to reveal the big picture. Hopefully, future works can increase the data set there. So, previous studies have found evidence that opal scavenging has the potential to significantly influence sedimentary protactinium thorium location, at some locations, including the Equatorial Atlantic and the South Atlantic. We have carried out simple linear correlation analysis on each of the sediment records here with the corresponding opal flux, and we found significant positive correlations in those marked by the star symbols. I didn't show the correlation plots here, but I do have it in my laptop here if you're interested to see the correlation plots after this. So, the remaining 10 deep Atlantic records, they review coherent changes in the West and Northeast Atlantic, shown in the top plot there. The remarkable agreement between the records from the West and the Northeast, this region, suggests a large-scale single control, which I think is most likely the Atlantic circulation. The trends are consistent with circulation slowdown during the North Atlantic coast stadias, Henrik Stadia 1, Younger Dryas, and resumptions during the boiling Araroid interstadia and the beginning of Holocene. In contrast, the persistently low values in the sediment cores from the low latitude East Atlantic actually reflects continual net protactinium export in that region. Again, given the limited time of this talk, I won't discuss the details here, but we do have some ideas on this observed trend, which should be considered in future protactinium thorium reconstruction work. Right, so from the West and Northeast Atlantic records that reflect large-scale pattern of Atlantic circulation change, we have constructed a composite record, a composite curve, the black curve, by computing a 9-point moving averages of the combined data set of the selected sediment cores. And an important feature that shows up on the composite curve is the major increase in protactinium thorium, indicative of Atlantic circulation slowdown from the LGM to the HS1. The inferred reduction in Atlantic circulation here began at about 18.5 thousand years ago, and this timing agrees very well with modeling results generated by our collaborator, Ruze Ivanovic. These new exciting results are part of a bigger modeling study examining the mechanisms at work between ocean, climate, and ice sheet system during the last glacier termination. If you want to know more about the modeling study, visit the poster, information there. At the bottom, right, I have only 1 minute left, so I'm going to skim through the bottom bit. So there are basically evidence for ice rafting from Eurasian ice sheets and Laurentide ice sheet, and the take-home message is that basically the relative timing of these records support the case that Eurasian freshwater-driven Atlantic circulation slowdown leads to major ice rafting from the Laurentide during the last glacier termination, and the Laurentide freshwater forcing in turn provide a positive feedback to further reduce Atlantic circulation at late HS1. So this leads to a slightly wordy conclusion slide. I hope I can have just half a minute, to quickly introduce an upcoming cruise to the Labrador Sea and Greenland coast this July. There will be a sort of complementary analysis with focus on the silicon isotope, but one of the main sampling focus is the coastal open ocean transit in the north. We'll be acquiring seawater, particulate, and sediment samples for 230 thorium analysis. If you have some great science idea on thorium in this region, feel free to talk to me afterwards. Now, back to the conclusion slide, and thank you very much for listening.